lecture is completely devoted only one method, the steepest descent method, one of the most ancient and one of the most popular optimization algorithm to solve an unconstrained optimization problem.
Neatly, the agendas of this lecture are as follows. At first, we will derive the steepest descent method. After the derivation, we will get to know the iterative formula for identifying the iterative sequence by the steepest descent method. Then we will get to know whether a scaling of the variables or a transformation of the variables will affect the steepest descent formula or not. Then we will get to know the global convergence of the steepest descent method. In between, we will find a typical property of the steepest descent method, that is the zigzagging phenomena, in which we will find that the consecutive direction of movement in steepest descent method are perpendicular to each other, and due to this zigzagging phenomenon, steepest descent method is a very slow method, especially when the objective function is ill conditioned. And finally, we will get to know a Barzilai-Borwein modification of the steepest descent method to improve the efficiency of the steepest descent method. Let's start. Before getting into the derivation of the steepest descent method, let me give you a broad overview of the optimization methods for solving unconstrained optimization problems. Let's suppose we are given a function of several variables and we wanted to find a minimizer or a minimum point of the function. And let's suppose this is a function of just two variables, and geometrically let us look how the direction of movements in any optimization process looks like. For that, let us try to draw out the surface of the function f, which we consider a function of two variables, so that we can graph out the function in the 3D space. Let's suppose the surface of the function z is equal to f x1 x2 is this surface, and in the x1 x2 plane the level curves of this function are given by the projection of the curve of intersection of the plane z is equal to some value, say c, with the surface of z is equal to f x1 x2. Here for this plane z is equals to c, the curve of intersection with the surface of z equals to fx1 x2 is, let's suppose, this curve and this curve. Now you take the projection of these two orange curves in the x1 x2 plane. You will get the level curves of the function z equals to fx1 x2 for the level z is equal to c. So here the points on this curve and on this curve are the points on which the function value is equal to c. Now you keep moving up and down this plane z equals to c, and accordingly take the intersecting curves of z equals to c with z equals to fx1 x2, and keep on taking the projection of those intersecting curves. You will get the level curves of the function f x1 x2. So for different values of c's, the level curves of the function z equals to fx1 x2 will look like all these sorts of curves. These are all level curves of the function z equals to fx1 x2. Now if we look at these level curves in the vertical plane of x1 x2, that means you just consider to draw out these level curves of the function z equals to fx1 x2 in the plane of x1 x2. The level curves will look like all these sorts of curves. I have drawn here the same curves that we have gotten over here. These are our level curves of the function f(x1, x2) for different values of c. The inner curves are the level curves with the value of c smaller and smaller, and accordingly this particular point and this particular point are 2 points of local minimum of the function f. And to reach at this local minimum in an optimization method, what we do, we start our process from an initial point, let's suppose x naught, and then we consider to move along a descent direction, and we take a step length of amount, let's suppose alpha naught. We reach at this point, then again reaching at this point, say x1, we take a descent direction, let's suppose d1, and an amount of step length, let's suppose this much amount of step length we took off. Then we will reach at the point x2, and then reaching at x2 we will again find the descent direction, we will reach at the next iterative point x3, and so on. So in this way we keep moving in an optimization method, and finally we expect to reach at a local minimum of the given function. And broadly optimization methods get differed by different way of choosing these descent directions and the step lengths. The available optimization methods are broadly classified into two parts: the methods using derivative and the methods not using derivatives. By using derivatives, we mean in finding the descent directions for the particular method, we do use the gradient information or the first order partial derivatives of the function. And the methods not using derivative are devised in such a manner that the iterative points are evaluated with the help of only the function values. No use of partial derivative of the function or higher order derivatives of the function are used in the methods of not using derivatives. In the methods which use derivative, there are two kinds of methods, where in the first kind we keep those methods which use only the first order partial derivative information of the function or which use the gradient of the function. And in the second kind we keep those methods which use the gradient as well as the Hessian of the function. In the methods not using derivative, we also have broadly two kinds of methods. In the first kind, we keep the non-smooth methods. Those methods are for those functions which are not differentiable. That is, these kind of methods are applicable only for non-differentiable or non-smooth functions. And hence these methods are named as non-smooth methods. In non-smooth methods, as the derivative of the function is not available, we use the information of subderivative or subgradient of the given function. So in the non-smooth methods, we broadly keep the subgradient methods. Subgradient of a function are those vectors which mimic the gradient of the function f. And in the second kind, no derivative or subgradient are used. That is, in these kinds of methods, using only the function values, no derivative information or no subgradient information of the function is used. The methods which use the subgradient or the gradient of the function, that means these non-smooth methods and using this gradient, these two kinds of methods are called as first order methods because they use the first order partial derivatives or first order subgradient of the function. For an elegant reference for first order methods in optimization, I would like to refer you the book by Amir Beg entitled First Order Methods in Optimization, which came out through Siam in the year of 2017. The methods which use both the gradient as well as the Hessian are called second order methods because they use partial derivatives of the function up to the second order. In this course, we will look into only one first order method, that is the steepest descent method, and we will consider quite a few second order methods such as Newton method, quasi-Newton methods, etc. But no non-smooth method or no method not using derivatives will be described in this course. But I will mention here a few methods that use only the function values. One of the popular most method for the methods which use only the function values is the Nelder-Mead method. And another few popular methods that use only the function value are cyclic coordinate method, the Hook and Gibbs method, and another method is the Rosenbrook's method. For a reference of the Nelder-Mead method, I would like to refer you the original paper by Nelder and Mead entitled A Simplex Method for Function Minimization. It came out in the year of 1965. For all these three methods, cyclic coordinate method, Hooke-Gibbs method, and Rosenbrook's method, I would like to refer you the book by Barzilai-Borwein that I have referred earlier in this course also, entitled Nonlinear Programming Theory and Methods. In cyclic coordinate method, what we do is we consider the direction of movements are the directions along the direction of the vectors in the standard basis. That means you consider the standard basis of the n-dimensional Euclidean space. Then we start from a given initial point x naught. Then at the point x naught, we consider to move along the direction of E1 after taking a fixed amount of step length along the direction of E1. We move along the direction of E2 and you keep moving along the direction of E3 till end up at En, and at the end of moving along the direction of En you will reach at the next iterative point, say x1. Now reaching at x1, we will again consider all the directions of the standard basis. You move along the direction of E1, then along the direction of E2, and finish visiting all the directions U1, E2 till En, reach at the next iterative point x2, and so on. So in this way, in the cyclic coordinate method, we keep visiting along the directions of the axis or the directions of the standard basis of the n-dimensional Euclidean space. From the current iterate xk, after visiting all the directions u1, e2 till en, taking a step length of a fixed or a constant step length, you will reach at the next iterative point xk plus 1, and so on, and accordingly you will get a sequence of iterates xk. You keep generating this xk as long as you are not getting a stationary point of the function. In the Hooke and Gibbs method, what we do is as follows. We notice that if we apply the cyclic coordinate method for a function whose level curves are, let's suppose, of this type, so that they have some sharp edged valley. Let's suppose we have some sharp edge like this point on the level curve of the function. In the cyclic coordinate method, we notice that it may so happen that in visiting the directions of the axis, we may reach at a sharp edge of the level curve of the function. At this surface, we notice that the direction E1 is not a descent direction because the function values gets degraded inside this curve. Like here, while drawing the level curves, we notice that if we are at a particular point, let's suppose over here, then the function values are not degrading along these directions, but they are degrading inside these inner curves. Like here you look at these level curves, then you notice that inner curves are the level curves on which the function values are getting lesser and lesser, and therefore we see that after reaching at this sharp edge, the function value is not degrading along the direction of the axis. So in this case, what we do is that from the point x naught, or let's suppose from the point xk, let's suppose we are reaching at this point xk plus 1 at the end of visiting all these directions of the standard basis, and we are observing that this xk plus 1 is a sharp edge of the level curves. Then as the function value at xk plus 1 is smaller than that of xk, what we consider? We consider the direction of xk plus 1 minus xk. And we notice that we may feel if we move along this direction, then the function value may be degraded, because at the point xk plus 1 the function value is smaller than that of at the point xk, and hence the direction xk plus 1 minus xk may be thought of as following the pattern of decrease of the function. That means if you move along this direction, the function value may be degraded. So this direction xk plus 1 minus xk is called a pattern direction. So in Hook and Jeeves method, what we do, starting from the current iterate xk, we explore the directions of all the axes. That is, we explore all the directions e1, e2 till en of the n-dimensional Euclidean space. Then reaching at the point xk plus 1, we consider the direction xk plus 1 minus xk, and along this direction we consider a step length of some amount. Then we reach at the next iterative point. So the next iterative point from this xk, we consider the point over here xk plus 1, and we denote this xk plus 1 as xk plus 1 dash. So this xk plus 1 dash is an intermediate point that is found after exploring all the directions of the axis. So the Hook and Jeeves method is comprised of two particular steps. The first, exploratory research, that explores all the directions of the standard basis, plus it considers a pattern search, and then it finds the next iterative point. This is how the Hook and Jeeves method works. Now in the Rosenbrook method, what we do is, instead of considering the standard basis as the direction of movements at the given current iterate xk, we consider to generate a set of n orthogonal directions d1, d2 till dn, maybe by using some method, the popular Gram-Schmidt method. And then after generating these n many orthogonal directions, we move along the direction d1, d2 till dn, and then visiting all the directions d1, d2 till dn, we reach at the point xk plus 1 dash. Then after reaching at the point xk plus 1 dash, we consider a pattern search along the direction xk plus 1 dash minus xk. So along the direction we take a step length and we reach at the next iterate as xk plus 1. And then after reaching at the point xk plus 1, we again consider to generate a new set of n orthogonal directions. We move along those new n many orthogonal directions, reach at the point xk plus 1 dash, take a pattern search, and then keep moving. This is how the Rosenbrook's method works. For a detailed description of cyclic coordinate method, Hook and Jeeves method, and the Rosenbrook's method, you please visit the book by Barzilai-Borwein and Setti. You will find a nicely detailed discussion on these three methods. Here I would like to mention that all these three methods, cyclic coordinate, Hook Jeeves and the Rosenbrook's method, have global convergence property, provided the minimum of the objective function f along any line in the Rn space is unique, and the sequence of points generated by those algorithms is contained in a compact set. Provided these two conditions are true for the objective function, all these three methods are globally convergent. Now next I will move towards the real agenda of this lecture, that is the steepest descent method, that falls into this category, the method which use only the gradient of the function. Let me now move towards deriving the steepest descent method. Let us suppose we are given a function of several variables and the function has continuous first order partial derivatives. Now to find a minimum of the function f, we start the process with a given initial point, say x naught, and then we move along the direction of most rapid decrease at the current iterate. For the current general iterate, say xk, the direction of movement dk is chosen so that the direction dk is the direction of most rapid decrease or the direction of steepest descent of the objective function. This direction dk of most rapid decrease or the direction of steepest descent is identified as follows. We notice that the rate of change of the function value at the point xk along the direction dk is given by the directional derivative. And as the function f is continuously differentiable, the directional derivative of the function f at the point xk along the direction, let's suppose a direction of unit length, is given by the gradient at the point xk transpose d hat. We wanted to choose this dk, the direction of movement, as one of these d hat for which this directional derivative has the minimum most value. So here we wanted to find then one d hat for which this value is minimum. Now to find a minimum most value of this directional derivative, we employ here the Cauchy-Schwarz inequality. By the Cauchy-Schwarz inequality, we see that we have the absolute value of the gradient at xk transpose d hat is less than or equal to norm of the gradient times the norm of d hat, that is equal to 1, and hence the gradient at xk transpose d hat is greater than equals to negative of the norm of gradient of fxk. And we see that the equality here happens when d hat is chosen to be the direction if d hat is equal to the direction of negative gradient. As d hat is a unit vector, we divide this direction by its length, that is norm of grad fxk. And hence a solution to this problem is the direction dk, which is the unit direction along the negative gradient. Then you choose this direction dk to be the direction of negative gradient. So negative gradient is the direction of most rapid decrease of the function f. And once the direction of most rapid decrease or the direction of steepest descent is identified, we take a step length of amount say alpha k along the direction dk and we proceed to the next step given by xk plus 1 is equal to xk plus alpha k dk. Now reaching at the point xk plus 1, again you consider the direction of negative gradient of the function, and along that direction of steepest descent you take a step length of amount alpha k plus 1, you reach at then next iterative point xk plus 2. You keep generating this sequence of iterates unless and until you get a point xk at which the gradient of the function is having length lesser than a threshold or a tolerance level. This is what exactly the steepest descent method is, and here during the derivation we pre-assume that this gradient is non-zero at the point xk. If this is equal to 0, then the point xk is returned to be one of the stationary points of the function f. That is what we exactly endeavor to reach at. So here across the iterations, when we generate by the steepest descent method, we pre-assume that the gradient of f at the point xk is a non-null vector. Now here you might ask that how one got an idea of this steepest descent direction method. To answer this question, we notice the derivation that we endeavored to find one direction dk, that is the direction of most rapid decrease of the function, and you move along the direction of most rapid decrease or the steepest descent and keep generating the sequence of iterates. So as this direction dk is the direction of most rapid decrease, and thus maybe one got the idea of moving along the direction dk and generating this method steepest descent. However, there is also one another interpretation of how one got an idea of this steepest descent direction method, that is as follows. We see that if we take the function f, the objective function, a function that has second order continuous partial derivatives, then the Taylor's expansion of this function f about the current iterate xk gives us the approximate equation fx approximately equal to f xk plus gradient of f at xk transpose x minus xk plus half of x minus xk transpose the Hessian of f at xk times x minus xk. Now if we replace this Hessian by the matrix some scalar multiplication 1 upon t times the identity matrix of order n, where this t is a real number, a scalar, then you consider an approximation of the function f at the current iterate xk is equal to, say, qkx given by the expression fxk plus gradient of f at xk times x minus xk plus 1 by 2t. Now you replace this Hessian by this matrix, you will get here norm of x minus xk square. So we get a quadratic approximation of the function f at the point xk as the following expression. Now after taking this approximation, the next iterative point xk plus 1 is chosen to be the minimizer, the minimum point of this approximation function. So to find the next iterative point xk plus 1, we try to find a minimum point of this approximated function qkx. Now to find a minimum point of the function qkx, we go for solving the equation for first order necessary optimality condition. The first order necessary optimality condition is given by the gradient of qkx is equal to the null vector, that is we obtain the gradient of f at xk plus 1 upon t x minus xk is equal to the null vector, that is we get the point xk minus t times gradient of fxk as a possible minimum point of the function qkx. Now we consider this expression as the next iterative point from the point xk. So we take the expression of the next iterative point xk plus 1 as this expression, and you notice that this expression is exactly the same expression that we have derived over here, that xk plus 1 is equal to this one together with the dk is given by this negative gradient, and hence this is how one might have gotten the idea of steepest descent direction method. Now let me neatly write out the algorithm for the steepest descent method. In the algorithm of steepest descent method, let's suppose we are going to find a minimum point of the function f. So we are given a function f of n variables, which we call as the objective function, that is known to have continuous first order partial derivatives. And let's suppose the initial point to start the method is x naught, and the tolerance level to terminate the process is, let's suppose, epsilon. Once these three things are provided, we move to the main steps to generate the sequence of iterates by the steepest descent method. In the first step, we initialize the iteration counter k to be equals to 0, where this k is referred as the iteration number, and then we move to the next step, where we at first check whether the gradient of the function f at the current iterate is less than epsilon or not. If not, then we go for identifying a descent direction dk, given by dk is equal to the negative of the gradient of the function f at xk, and then along the direction dk we choose a step length alpha k, given by the exact line search method or one of the inexact line search methods. After identifying this alpha k, we update the current iterate by xk plus 1, which is given by xk plus alpha k dk. Then we increase the counter number k by 1 unit. So we take k to be now k plus 1, and then again check whether at the revised iteration point xk plus 1 the norm of the gradient is less than epsilon or not. If not, then again keep on executing all these steps unless and until you find a point xk at which gradient of fxk is less than epsilon. So while norm of gradient of fxk is greater than equals to epsilon, you go for executing all these steps, and at the end of this while loop we get the output as the point xk, which is possibly an optimum point or a stationary point of the function f. Now after this algorithm, we immediately look that as the direction dk is a direction of steepest descent and hence a descent direction, this method certainly is generating the sequence of iterates xk's for which the sequence xk has a descent property. So we note that the steepest descent method, which we abbreviate as SD, the SD method has the descent property. By that we mean if xk is the sequence of points generated by the steepest descent method, the sequence xk has the property that the function value at the consecutive points are satisfying fxk plus 1 less than fxk. Now here I must mention the innovator of this steepest descent method. The person who invented this steepest descent method is none other than Augustin Louis Cauchy, one of the great mathematicians. He derived this method in the year of 1847, and its first partial mathematical analysis was done almost after 1 century in the year of 1951 by Forsythe and Mochkin. And this steepest descent method or the Cauchy method is one of the most popular methods till today due to its simplicity. That just you consider the direction of steepest descent, move along the direction, keep moving. At the end of the day, you will be certainly reaching at a point that is at least a stationary point of the function f. The simplicity of the steepest descent method is not only the reason that the Cauchy method is most popular among the theoreticians as well as practitioners, but there is also another reason, the complexity bound, that to reach at an epsilon precise solution for the equation gradient of f is equal to 0, there is a ready-made bound that after certain number of iterations you will be able to reach at a point at which you will have the gradient of the function is having norm less than epsilon. You pass the value of epsilon, then readily you will be able to identify exactly after how many steps you will be able to reach at a point xk for which this inequation is true. And most surprisingly, this inequation is true starting from any initial iterate point x naught. You start from any arbitrary point x naught from the n-dimensional Euclidean space, keep generating the sequence of iterates given by the steepest descent method, then exactly after these many number of iterations, you will be able to find a point xk at which this norm is less than epsilon. Towards the end of this lecture, we will get to know a surprising result for a general convex function that states that if you start your steepest descent method from a given point, given any arbitrary point x naught from the n-dimensional Euclidean space, then at the current iterate xk, the difference between the function value at xk and at a point x bar, which is a minimizer or a minimum point of the function f, is less than c naught divided by k, where k is the number of iterations that you have executed so far. So after k many iterations, if you have reached at the point xk, this inequality is true, where this c naught is a constant that depends on the initial point x naught. And hence, at the current iterate, you will be able to estimate how far you are from the minimum point of the objective function f. From this inequality, you can estimate that to reach an epsilon precise solution to this fx bar, you need exactly c naught divided by epsilon many iterations. After these many iterations, obviously fxk minus fx bar is less than epsilon. So to reach at an epsilon neighborhood of a minimum of the function f, you require precisely c naught divided by epsilon many solutions. Due to this fascinating result of a priori estimating the number of iterations you require to reach at a global minimum of the function, the steepest descent method is possibly, although being very ancient, but most popular so far among mathematicians as well as among practitioners. Next, we will consider a numerical example to be executed by the steepest descent algorithm. But before that, let me quickly visit the scaling effect, scaling of variables effect for the steepest descent direction. Let us suppose we are given a function for which the generic variable is x. It is a function of several variables. Let's suppose of n variables, and let's suppose the original variable space is the space of the variables x's. So here we are in the x space, and let's suppose we are applying a transformation of the variables by a transformation matrix, say capital T, which is a non-singular matrix. By the transformation x hat is equal to tx, let us suppose we have reached to the space of x hat. In the x space, the function is given by fx, and in the x hat space, the function fx has been changed to f hat x hat, which is given by the function value at x, or in terms of x hat, this is f of t inverse x hat. Here this transformation matrix T is invertible. Now to compute the steepest descent direction at the current iterate xk, we compute the gradient in the x space, gradient with respect to x of the function fx. In the x hat space, the gradient you all know is given by, in terms of the gradient in the x space, the expression T inverse transpose gradient x of the function fx. And hence at the current iterate xk hat in the x hat space, the steepest descent direction, say dk hat, is given by negative gradient of f hat at the point xk hat. Here this hat has not to be confused with being unit vector. This hat is just on the x hat space. So this hat here dk may not represent a unit direction. So here this dk hat is given by this expression, which in terms of the gradient in the x space is equal to T inverse transpose the gradient with respect to x of the function f at the point xk. Now with this dk hat, if we wanted to execute the pure steepest descent iterate, by pure steepest descent iterate we mean here you employ this alpha k to be is equal to 1. The step length, once alpha k is taken to be the unit length alpha k is equal to 1, then we call this xk plus 1 the pure steepest descent iterate. And accordingly, this steepest descent method is called pure steepest descent method when we consider the value of alpha k is equal to 1 across all k values. K is equal to 1, 2, 3 and so on. Now in the scaling effect, let us see if the pure steepest descent iterate in the X space can be revived from the calculation of the pure steepest descent iterate in the X hat space. In the X hat space, the pure steepest descent iterate xk plus 1 hat is given by xk hat plus dk hat. And now let us see if this xk plus 1 can be revived from taking the inverse transformation T inverse on the vector x hat k plus 1. Notice that here this xk plus 1 hat is given by xk hat minus T inverse transpose gradient of f at xk. Now we apply T inverse on both the sides and we get this T inverse of xk hat is xk. Then we have here T inverse times T inverse transpose gradient x at xk. And due to the appearance of this expression, we notice that this T inverse xk plus 1 hat is not equals to the xk plus 1 in the x space. That is, it is not equal to xk minus gradient of f at xk. And thus the steepest descent method is dependent of transformation of variables. However, if we take the matrix T is such a matrix that is orthogonal, then you notice that this expression here is an identity matrix, and hence when T is an orthogonal matrix, then the steepest descent method is independent of scaling of the variables. We do write it here neatly that in general, that means for a general given transformation matrix T that is just invertible, the steepest descent method is scaling dependent to scaling of the variables. However, if the transformation matrix T is orthogonal, the steepest descent method is independent of scaling of variables or scale invariance. By here, this scaling dependent or scale invariance in these two sentences, we mean scaling of the argument variable x. Now, if we do a scaling of the dependent variable, that is, let us suppose we are applying a scaling of the function value by a factor, say a scalar c, say constant c times fx, and let us suppose this function is the function psi x. After the scaling of the dependent variable z is equal to fx, let us compute the steepest descent direction for this scaled function psi and the original function f. The steepest descent direction at the current iterate xk for the scaled function psi is given by the negative of the gradient of psi at xk, which is simply c times negative gradient of the function fxk, which we note that gives the same direction, the descent direction for the original objective function f, provided this c is positive. So if this c, the factor, is positive, then the steepest descent method is independent of the scaling of the dependent variable z. Now we will consider a numerical example where the steepest descent method will be executed. For the example, we consider the function a function of two variables x1 x2 given by half x1 square plus 9 by 2 x2 square. This is a function of two variables having continuous first order partial derivatives. Now we consider to apply the steepest descent method on this function from the initial point x naught is equal to the point with coordinates 9 and 1, and we consider the tolerance level, say epsilon is equal to 0.01. And let us suppose the step length in this steepest descent method will be chosen by the exact line search. Now to find the next iterative point x1, we go for calculating the steepest descent direction, which is given by the gradient of the function. As across the iterations, we will require the gradient of the function to be executed. So let me consider to identify the gradient of the function at a general point x1 x2. The gradient at a general point is given by x1 9x2. Now let us go for executing the first iteration, in which we have the iteration counter k is equal to 0 and the steepest descent direction d naught is given by negative of the gradient at 9 1, which is equal to the coordinate minus 9, and the step length alpha naught is given by argmin of the function phi, where the function phi is given by phi alpha is equal to f of x naught plus alpha d naught, which is f of 9 minus 9 alpha 1 minus 9 alpha, and hence it is half of 9 minus 9 alpha square plus 9 by 2 into 1 minus 9 alpha square. Therefore, to execute alpha naught, which is a minimum point of the function phi alpha, we solve for phi dash alpha is equal to 0. That gives this equation, and hence we get alpha is equal to 1 by 5, and at alpha equals to 1 by 5, you please check that the second order derivative of this function phi is a positive quantity, and therefore this alpha naught is given by 1 by 5. So the next iterative point x1 is given by x naught plus alpha naught d naught, which is equal to 9 1 plus 1 by 5 minus 9 minus 9, which gives us finally the point 9 minus 1 times 0.8. So at the end of the first iteration, we get the next iterative point x1 given by 9 minus 1 times the scalar 0.8. Now before proceeding to the next iteration, we check whether the gradient of the function f at x1 has norm less than 0.01 or not. You will find that this is not less than 0.01. So we proceed to the next iteration, the iteration 2, where I put a home task here that you please check the next iterative point x2 is given by 9 plus 1 here, then times 0.8 square. Further, in the next iteration, iteration 3, you please check that the next iteration x3 is given by x3 is equal to 9 minus 1 times 0.8 cube, and in general we will find that at the kth iteration the iterative point xk is given by 9 minus 1 whole to the power k times 0.8 whole to the power k. You please cross check this formula for all values of k is equal to 0, 1, 2 and so on. Here for this example, if you go for identifying the trajectory of movement of the steepest descent points, you will find that the steepest descent points in the space of the variables x1 and x2 will look like as follows. Let's suppose this is the location of the point with x1 value is equal to 9, and let's suppose the value of 1 x2 is equal to 1 over here. So we are starting at k equals to 0 at this point x naught, which is the coordinate 9 1, and then the next iterative point is given by 9 minus 1 times 0.8. You will find that its location is somewhere over here. So we join these 2 points, this x naught to x1, and this is the direction d naught along which we moved in the first iteration. Then we look at the point x2. x2 has coordinate 9 1 times 0.8 square, so it will be above the x1 axis somewhere over here. Here is the location of x2. Now you join x1 to x2. This is the direction along which we moved to find the iteration x2. Then you keep finding x3's location, then x4, afterwards x5, then x6 and so on, which gives us a zigzagging path along which the steepest descent method moved to find the iteration sequence xk. Here you will find that this direction d1 is perpendicular to d2, d2 is perpendicular to d3 and so on. In general, I would like to give a home task here that you please cross check that the consecutive directions dk and dk plus 1, they are perpendicular to each other. That means you will find that dk plus 1 transpose dk is equal to 0. This is actually not a surprise for this particular example. This is not a coincidence, but this is actually a general fact for a steepest descent method. that you apply steepest descent method on a function that has just first order continuous partial derivatives, you will find that the sequence generated by the steepest descent method has the property that the consecutive directions dk plus 1 and dk, they are perpendicular to each other, and hence the path of movement follows a zigzagging path. Now next we'll go for proving this zigzagging phenomenon for the steepest descent method for any given function of several variables. Before moving to the zigzagging phenomenon, let me just give you a home task that for a quadratic function fx is equal to half x transpose qx plus b transpose x plus c, where Q is a positive definite symmetric matrix. You please try to figure out the exact step length of the steepest descent method. You will find that the step length given by the exact line search for this quadratic function is given by alpha k is equal to gk transpose gk divided by gk transpose q times gk, where this gk is a common notation in optimization theory which represents the gradient. This g is for gradient of the function f at xk. So I would like to give you a home task here that you show that the exact step length, by exact step length we mean the step length given by the exact line search, and you please figure out that this alpha k is given by this formula. I am keeping it as a home task. Let me also give you a home task that you please find a lower bound of the iteration number k for which this steepest descent path will reach at an epsilon neighborhood of the point origin. Origin is the exact minimizer of this function that we have taken over here. And for this function, we have identified that the sequence of iterates for general k is given by this expression. Now I would like you to give you home task that find the least possible k for which norm of xk is less than epsilon, or find the least value of k for which the gradient of f is less than epsilon. That is, you find the least possible value of k at which the steepest descent method will get terminated, for which we have gradient of f at xk is less than epsilon, and then you put the value of epsilon as 0.01. Then you please try to figure out that how many iterations are required to reach at a stationary point for this particular example that we have drawn over here, and that will give you a feeling that how slow is this steepest descent method. You will require a handful number of iterations, then only you will be able to reach inside an epsilon neighborhood of a stationary point. And this handful number of iterations is due to this zigzagging phenomenon. Initial steps are quite large step length, but when we move towards the solution, the stationary point, this zigzagging phenomenon is so prominent, you will require quite a bit number of iterations to reach at a stationary point. And this is very typical for the steepest descent trajectory or the steepest descent path, that initially the steepest descent method may take larger steps, but when we reach at the solution, the step lengths are so small that you will require considerably large number of iterations before reaching at a stationary point. This small step length when k is large and perpendicular directions of movement in steepest descent method makes the method terribly slow when reaching towards a stationary point. Let us now prove the zigzagging phenomenon for a general function that is known to have continuous first order partial derivatives. Let us suppose xk be the sequence of iterates generated by the steepest descent method with exact line search. Then for any k, we have the consecutive directions of movements, that xk plus 2 minus xk plus 1 is perpendicular to xk plus 1 minus xk. Let us now prove this result. In proving this result, we notice that from the iterative formula of the steepest descent method, we have the inner product or dot product of these two vectors, xk plus 2 minus xk plus 1 and xk plus 1 minus xk is equal to alpha k times alpha k plus 1 times gradient of f at xk transpose gradient of f at xk plus 1. So to prove the result that these two vectors are perpendicular, we have to prove that these two vectors are perpendicular to each other. Now to prove that these two vectors are perpendicular to each other, we note that the step length alpha k given by the exact line search is given by a non-negative scalar that minimizes the function phi, or let me write phi k because we are endeavoring at the point xk. Better to write this as phi subscripted k of the function f at the point xk plus alpha dk, where this dk is the steepest descent direction gradient of f at xk. As the function f is continuously differentiable, the function phi k is also continuously differentiable, and hence once this alpha k is a minimizing point of the function phi k, we must have phi dash k at alpha k is equal to 0, which gives us by the chain rule gradient of f at xk plus alpha k dk transpose dk is equal to 0. Here I would give you a home task, or rather look at one of the previous lectures in which we have proved that for this expression f of xk plus alpha dk, with the help of chain rule, you will find that its derivative with respect to alpha is given by this expression. You please make a recapitulation of this formula and figure out that this expression is a correct expression of phi k dash at alpha k. And hence we get here that this gradient of f at xk plus 1 and this direction dk, which is the direction of negative gradient of f at xk, and then we write here gradient of f at xk is equal to 0. And therefore what we get, that inner product of these two vectors, the consecutive directions of movements in steepest descent method are perpendicular to each other, because this expression is equal to 0, and that proves the result. Now next we will move towards the global convergence result of the steepest descent method. Before the global convergence result, let me write here a neat observation, that we see that the function that we have taken up over here in this example, it is a quadratic function with positive definite Hessian. But the steepest descent method for this quadratic function required more than n number of iterations. N is the number of variables, here n is equal to 2. So for this example, we notice that although this is a function of two variables, a quadratic function, but the steepest descent method for this function required more than two iterations to reach at a stationary point, and therefore steepest descent method does not have quadratic termination property. As a note here before zigzagging, let me write here that the steepest descent method does not have quadratic termination property. That means steepest descent method does not converge within n number of iterations to a stationary point for a quadratic function of n variables. However, if we take a quadratic function, a very special kind of quadratic function that has the level curves fully circles instead of ellipses, then the steepest descent method converges in one iteration. Let us prove this fact in an example that the SD method converges in one iteration for the function f(x) given by the Euclidean norm of x minus a square, where a is a given point in the n-dimensional Euclidean space. Here throughout the course, as and when we are writing x, we shall mean that x is having n many components. X is a generic variable of the n-dimensional Euclidean space. So here this example neatly states that the steepest descent method converges in one iteration for this function. However, if we consider the function f that has level sets or level curves, ellipses or ellipsoids, not the spheres or circles, then the steepest descent method may take infinitely many iterations to reach at a stationary point. Let us now prove these two phenomena, that the steepest descent method converges in one iteration for this function. However, for a function f with ellipsoidal level sets, the steepest descent method may take infinitely many iterations to reach at a stationary point. To prove the first fact, we see that for any given x naught in Rn, the steepest descent direction d naught is negative of the gradient at the point x naught, which is given by negative of x naught minus a. And now if we take the step length in the steepest descent method given by exact line search, then we see that the alpha naught value is argmean of the function phi alpha, where phi alpha is given by f of x naught plus alpha d naught, which is equal to alpha minus 1 square into x naught minus a square of it, and therefore the value of alpha naught is equal to 1, and hence the next iterative point x1 is given by x naught plus alpha naught d naught, which is equal to x naught plus alpha naught is equal to 1, d naught is equal to minus x naught plus a, which is equal to a. And we see that this a is the exact minimizer, a stationary point of the function f. So the steepest descent method with exact line search converges in one iteration for this particular quadratic function. Now to show that the steepest descent method may take infinitely many iterations, you can look at the example that I have given over here. Here you look at this steepest descent trajectory, and from here you can find that this norm of xk tends to 0 as k tends to infinity, and therefore to reach at the exact minimizer or a stationary point of the function, we require infinitely many iterations. Or in general, we may consider a function f. For example, we take a function of two variables x1, x2, that is given by half of x1 square plus lambda times x2 square, where lambda is a given real number, a constant greater than 1. We consider this function which is having elliptical contour or elliptical level curves. We will show that the steepest descent method takes infinitely many iterations to reach at a stationary point. Here for this function, you may quickly draw the level curves. The level curves of these functions are given by the ellipses having major axis length bigger than the minor axis, and therefore ellipse of this kind. For different values of c's, the level curves if x1 x2 is equal to c are given by some other ellipses, as this one, maybe for a bigger value of c you will get another ellipse like this, and so on. Here, as the value of this lambda gets bigger and bigger, the level curves becomes increasingly stiff in the x2 direction relative to the x1 direction. And here, this value of lambda actually identifies the condition number of the Hessian of this function f. We notice that the Hessian of this function f has eigenvalues 1 and lambda. And as lambda is greater than 1, the Hessian matrix is a positive definite matrix and a symmetric matrix, and hence the condition number of the Hessian of this function f is given by the formula of condition number of a positive definite symmetric matrix capital A, which is given by the ratio of maximum eigenvalue of the matrix A and the minimum eigenvalue of the matrix capital A. Here, for this function f, the Hessian has condition number at any point x is equal to lambda. So when lambda gets larger and larger, the condition number of this Hessian matrix is bigger and bigger, and hence for large value of lambda, this Hessian matrix is ill conditioned. In case we have chosen this lambda is equal to 1, then we have already seen that the steepest descent method converges in one iteration. But if you take the value of lambda greater than 1 or substantially bigger than 1, this function is going to have ill-conditioned Hessian matrix, and for this function we can show that we will require infinitely many iterations to reach at the stationary point, the origin for this function. To show this that it requires infinitely many iterations, let us find k plus 1th iterate from a given kth iterate xk. At the kth iteration point xk that has coordinates x1k, x2k, the descent direction, the steepest descent direction dk is given by negative gradient at xk, which is equal to negative of x1k and lambda x2k, and the step length along this direction dk, the exact step length alpha k, is given by, you please cross check, I am giving a home task here, the exact step length is given by x1k square plus lambda square x2k square divided by x1k square plus lambda cube x2k square, and therefore xk plus 1 is equal to xk plus alpha k dk is given by the coordinates, these coordinates, where this is the first coordinate and the second coordinate is this expression. Now from this expression of general iterate, we observe that if the steepest descent method is started with a point x0 having coordinates say x1 0, x2 0, for which let us suppose the ratio of x1 naught and x2 naught is equal to k, which is not equal to 0 say, then we see that the next iterate x1, which is having coordinates say x11 and x21, where this x11 and x21 are given by these two expressions. So if we take the ratio of x11 divided by x21, which is equal to, by these two expressions, minus lambda square x20 divided by x10, which is equal to minus lambda square by k. Then further, for the next iterate x2, which is having coordinates say x12, x22, we have x12 divided by x22. This is equal to minus lambda square times x21 divided by x11, which is equal to minus lambda square times k divided by lambda square, positive here. This is equal to k. Further, for the next iterate, again you can prove that the ratio of the coordinates is equal to minus lambda square by k. Or here you may get confused with this k with the iteration number k. Better let us replace this k by some other value, let's suppose beta. Better to replace this k by beta so that we will not get confused with this used k with the iteration number k. So here what we see that the sequence of values x1k divided by x2k, they alternate between the values beta and minus lambda square by beta. And ultimately we can show that norm of xk plus 1 tends to 0 as k tends to infinity. If we look at the locations of these points xk's in this contour, we will find that the points are fluctuating in between the lines x1 by x2 is equal to beta and x1 by x2 is equal to minus lambda square by beta. Let us draw these two lines in the level curves over here. Let us suppose this is the line x2 is equal to 1 by k x1, and suppose this line is the line x2 is equal to minus beta by lambda square into x1. Then if we would have started the initial iterate from this point, say, then the next iterative point will be on this line. Afterwards, the next iterative point will be on this line. Then by following a zigzagging path, the sequence of iterates will slowly reach at a stationary point of the function. Here, although my drawing is not perfect, here in a zigzagging phenomenon, the consecutive directions are perpendicular to each other. So here what we see that the sequence of iterates are fluctuating in between these two lines. And from here then we can sense the step lengths are getting smaller and smaller when we are reaching towards the stationary point of the function f. And by the slow progress towards the stationary point, the origin here, we notice that we will require infinitely many iterations to reach at the stationary point. To show this, that how slow this method is to reach at the stationary point, let us go for computing the ratio of the function values at the iterative points. Let me give you a home task that the sequence of iterates xk that we have derived over here, for this expression, you please prove that the ratio of fxk plus 1 and fxk is equal to some number ck square times lambda into lambda minus 1 square divided by ck square plus lambda cube times ck square plus lambda, where this ck is equal to x1k divided by x2k, where this x1k x2k are the coordinates of the current iterate xk. Now after showing this equation is valid, then you try to prove that this expression on the right hand side is maximized when the value of ck is equal to lambda square, and hence try to cross check that fx plus 1 divided by fxk is less than equal to lambda minus 1 square divided by lambda plus 1 square, which is certainly less than 1, and therefore this sequence fxk is a decreasing sequence and fxk converges to 0 as k tends to infinity. But here we notice that as this lambda value gets bigger and bigger, this right hand side, this portion is approximately equal to 1. So this ratio fxk plus 1 divided by fxk is almost is equal to 1 but just slightly smaller than 1, and this gives a sense that how slow is this sequence fxk to converge to the point 0. To find a least value of k for which fxk is less than certain precision epsilon, let us give us a home task that find a lower bound of the iteration number k for which fxk is less than epsilon for a given precision epsilon. You will find that the value of k for which fxk is less than epsilon is quite a large number, and when this lambda gets bigger and bigger, the lower bound of k gets larger and larger. So for high condition number, for high value of lambda, or for ill-conditioned Hessian, the steepest descent method takes large number of iterations to reach at a stationary point or a minimum value of the function f. Now next we'll go for the global convergence of the steepest descent method. In analyzing the global convergence of the steepest descent method, we recall here that a general descent method has global convergence. We have proven this fact that a general descent method has a global convergence. By that we mean we consider any descent direction dk to be employed in the current iterate xk. You consider any descent direction and then take a step length alpha k by the exact line search method or any of the inexact line search method. You move to the next iterative point. At the next iterative point you take a descent direction, any descent direction will work, and keep on moving, generating the sequence of iterates xk, where at each and every xk you employ any descent direction dk. Then you will find that this optimization method with any descent direction dk has global convergence. This result we have already proved. And now for the steepest descent method, we notice that the direction of movement dksd is a very special direction, that is the steepest descent direction and hence a descent direction. So the steepest descent method has global convergence property, that you start from any initial point x naught, then you generate the sequence of iterates xk. At the end of the day you will find that you have reached at a point at which the norm of the gradient converges to 0 as k tends to infinity. And therefore we neatly write here that as a general descent method has global convergence and the direction dksd is equal to negative gradient at xk is a descent direction, the SD method has global convergence. But here for the global convergence property of the steepest descent method, I must mention here that the objective function f must be such that the gradient of the function f is a Lipschitz function. So we consider here the function f is not only having continuous first order partial derivatives, but the gradient of the function f is a Lipschitz function with certain Lipschitz constants, say L, throughout the n-dimensional Euclidean space. Here this notation is very special in optimization theory. By this we mean the function f has continuous first order partial derivatives, then this one stands for the gradient that comprised of first order partial derivatives is a Lipschitz function with this constant capital L. So this inequality is true for the function f. Provided this inequality is true for the function f for every xy in the n-dimensional Euclidean space, or even in a restrictive set, you can also consider, instead of in this Rn, you could have also considered inside the convex hull of the initial level set L0. By the initial level set L0 we mean the set of points in Rn for which the function value is less than equal to the function value at the initial point x0. Inside this convex hull of L0, if the function f has continuous first order partial derivatives and the gradient of the function f is Lipschitz, under this condition we all know that a general descent method has global convergence, and hence steepest descent method is also having global convergence property provided the function f is C11L function. Now next we will go for identifying the rate of convergence or the performance of the steepest descent method. To identify the rate of convergence or the performance of the steepest descent method, we consider the minimization problem, the unconstrained optimization problem, with the objective function f is such that for which we have the global convergence property is a C11L function in the n-dimensional Euclidean space Rn, and also assume that the function f is bounded below. Now in estimating the rate of convergence of the steepest descent method, we will derive a few lemma before reaching at the final result on the rate of convergence of the steepest descent method. The first lemma towards the result of global convergence is a result from calculus for functions of several variables that states that let f be a twice continuously differentiable function and its Hessian has a norm that is bounded above by a constant, say capital L, and we consider this bounded aboveness of the Hessian is not in the entire n-dimensional Euclidean space, but let's suppose in a restricted space, that in the convex hull of the initial level set L0. By initial level set L0, we mean the collection of points in Rn for which the function value is less than equal to f at x0. x0 is the initial point to start the steepest descent direction method. Then we can prove that the gradient of the function f is a Lipschitz function with Lipschitz constant is equal to capital L. This result is straightly followed from the mean value theorem for vector valued function, because you notice that if we consider the norm of gradient of f at x minus gradient of f at y, then we see that by the mean value theorem for vector valued function, we will have, with respect to a matrix norm of the Hessian matrix of the function f at a point x hat, where x hat is a point in the line segment joining the points x and y. This norm times norm of x minus y. Now as the Hessian matrix has norm bounded by the constant capital L, we will have this quantity less than equal to L times norm of x minus y for every x and y in the convex hull of the set L0. Now here, to reach from these to right hand side this inequality, we have employed the mean value theorem for vector valued functions. For the mean value theorem for vector valued functions, you may please look at any calculus book, and for instance you may look at the classical analysis book by Apostol. Now next we will prove a lemma for a function that is C11L function in the n-dimensional Euclidean space Rn. The lemma states that let us suppose f is a function of several variables, that is C11L function in the entire n-dimensional Euclidean space. Then we can prove that the absolute value of fy minus fx minus grad of fx transpose y minus x is less than equal to L by 2 norm of x minus y square for every xy in Rn. The proof for this lemma 2 is as follows. Let us suppose we define a function phi, a function of one variable, given by f of x plus t times y minus x. As the function f is continuously differentiable, the function phi is then continuously differentiable, and the derivative of phi at t is given by gradient of f at x plus t times y minus x transpose y minus x, and therefore phi 1 minus phi 0 is equal to the integration of phi dash t dt, which in turn gives us phi 1 is equal to f of x plus 1 times y minus x, so fy, and this phi 0 is fx, and under this integration we will have this phi dash t, that is gradient of f at x plus t times y minus x transpose y minus x dt, which then can be written as integration 0 to 1, the integrand x plus t times y minus x. We subtract it with the gradient of f at x, take the transpose, times y minus x dt plus grad f transpose y minus x. Here we have subtracted this grad f x transpose y minus x, which is independent of t, and therefore we have added here this subtracted quantity, gradient of f x transpose y minus x, and therefore bringing this term on the left hand side and then taking the absolute value, we will get fy minus fx minus gradient of fx transpose y minus x is less than equal to integration 0 to 1. Then inside we will have norm of gradient of f at x plus t times y minus x minus grad fx multiplied with norm of y minus x. This norm multiplication is inside this integration, which then on the right hand side gives us, as the gradient of f is Lipschitz with constant L, we will have then this norm of this entire quantity is less than equal to L times norm of this vector minus x, and that gives norm of y minus x, multiply it with norm of y minus x, its square, integration 0 to 1, the rest out factor t dt, which is equal to L by 2 norm of y minus x whole square. That is what exactly this result states, that if f is a C11L function, then the absolute value of this entire expression is less than equal to L by 2 times norm of x minus y square. Now with the help of this result that we have just now derived, we shall now execute an estimate of the reduction of the function value by the movement from one point xk to the next point xk plus 1, where these xk plus 1 are generated by the steepest descent method. So we are now endeavoring to identify the reduction of function value by the movement of one step or one iteration of the steepest descent method. The result states that, let us suppose we are given an objective function, that is C11L function, in the n-dimensional Euclidean space, and suppose xk be the sequence of iterates generated by the steepest descent method. Then an estimate of the reduction of the function value, that is fxk minus fxk plus 1, is at least 1 by 2L times gradient of f at xk, its square. A proof of the result is as follows. As the function f is C11L function, then due to this previous lemma, we will have that this expression inside this modulus is less than equal to L by 2 norm y minus x square. Here in particular we take x to be the vector xk and y to be the vector, say xk plus alpha dk. Then we will have f of xk plus alpha dk is less than equal to f at xk plus gradient of f at xk transpose times x minus this vector, which gives minus alpha dk, plus L by 2 times alpha square into norm of dk square, which in turn gives us fxk plus L alpha square by 2 minus alpha times norm of grad fxk square. Now this inequality is true for any given alpha greater than 0. So by taking minimum over alpha on both the sides, we will get minimum over alpha greater than equals to 0 of fxk plus alpha dk is less than equal to the minimum of this quantity. You please execute. The minimum of this quantity, will be given by the minimum of L alpha square divided by 2 minus alpha. For its minimum, you take the derivative of this function. You will get alpha L minus 1 is equal to 0. So at alpha equals to 1 upon L, you will have the minimum of this function, because at alpha equals to 1 upon L, the second order derivative of this function is positive. And hence, you will have here on the right hand side fxk plus, at alpha equals to 1 upon L, we will have here minus 1 by 2L times gradient of fxk square of it. Here I must mention that I have taken here gradient of fxk because the dk in the steepest descent direction is negative gradient. When we consider taking minimum of this function over alpha greater than equals to 0, then we note that we get the point xk plus 1 given by the steepest descent direction method. So if xk plus 1 is less than equal to fx minus 1 upon 2L norm of grad f at xk square of it. This is what exactly we have written in this inequality. So in one iteration of the steepest descent method, the function value gets degraded at least an amount of 1 over 2L norm gradient of f at xk square of it. With the help of this result, the lemma 3, I will now state a result that identifies the rate of convergence, the Q rate of convergence of the steepest descent method. The result states that, let the objective function f be twice continuously differentiable near a local minimum, say x bar, of the function f. That means there exists a neighborhood of the point x bar in which the function f is twice continuously differentiable, where at the point x bar the Hessian of the function is positive definite. Now let us suppose the sequence generated by the steepest descent method be the sequence xk that converges to the point x bar. Then we can show that fxk minus fx bar is less than equal to gamma to the power k into fx naught minus fx bar, where x naught is the initial point to start the steepest descent method, where this gamma is a constant lying in between 0 and 1. Also, we can show that the norm of xk plus 1 minus x bar is less than equal to under root of capital M divided by small m times theta into xk minus x bar, where here again theta is a constant in between 0 and 1, and for small m and capital M I'll state later what are these small m and capital M. The third result is that the ratio of fxk plus 1 minus fx bar divided by fxk minus fx bar, this is less than 1 for every k, and the limit supremum of this ratio fxk plus 1 minus fx bar divided by fxk minus fx bar is less than equal to capital M minus small m divided by capital M, which is less than 1, where these capital M and small m are two positive numbers that satisfy 0 less than small m less than equal to lambda n less than equal to lambda 1 less than equal to capital M, where these lambda 1 and lambda m are largest and smallest eigenvalues of the Hessian of f at the point x bar. Now this result is a bit tedious to prove. I will rather give a reference for the proof of these three results. For the first and second part of this result, you please visit the page number 81, where you will find the theorem 2.2.8, page number 81 of the Sun and One's book that I have referred quite a few times in the previous lectures. For the third part of this result, you please look at the same book by Sun and One at the page number 125, theorem 3.17. By the third part of this result, we see that limit supremum of this ratio is a finite and definite quantity, and therefore the sequence fxk converges to fx bar with q order of convergence at least 1. Here also, from the second part, we notice that the sequence xk converges to x bar with q order of convergence at least 1. I write these two observations neatly as a note that the sequence xk converges to x bar with q order of convergence at least 1. The sequence fxk converges to fx bar with q order of convergence at least 1. And we can show there are functions for which the q order of convergence is precisely equal to 1. And therefore steepest descent method is commonly said as having q order of convergence is equal to 1. That is, steepest descent method has a linear rate of convergence. And therefore steepest descent method, although enjoys the global convergence property, but it is a slow method. And hence, from the discussion of steepest descent method so far, we see that the steepest descent method performs poorly, converges globally, but has convergence rate linear, and it is badly affected by ill-conditioned Hessian. We have seen one example in this lecture that if the objective function has Hessian ill-conditioned, then the zigzagging path of the steepest descent method takes infinitely many iterations to reach at a stationary point. So I write here that the steepest descent method has the good properties that it has descent property, it is globally convergent, but the bad properties are that the steepest descent method has linear rate of convergence, and as the steepest descent method has zigzagging phenomenon, the method is badly affected by ill conditioning Hessian. To alleviate the drawbacks of the steepest descent method, in the year of 1988, Barzilai-Borwein presented a two-point step-size gradient method based on two-point approximation to the second equation underlying the quasi-Newton methods. This Barzilai-Borwein modification of the steepest descent method is as follows. The method is found in the paper by Barzilai and Borwein, where the steepest descent method is modified in the following manner. We notice that the steepest descent iteration formula is given by xk plus 1 is equal to xk minus alpha k dk, where dk is negative gradient, which can equivalently be written as xk plus 1 is equal to xk minus dk times gradient of fxk, where this dk is the matrix alpha k times in. This in is the identity matrix of order n by n. Now here we choose the step length alpha k in such a manner that this matrix dk satisfies the quasi-Newton property. The quasi-Newton property will be discussed maybe one or two lectures later, but here I will use the quasi-Newton property, which states that you take dk in such a manner that dk satisfies the quasi-Newton equation, that dk times yk minus 1 is equal to sk minus 1, where this vector yk minus 1 is the gradient of the function f at the point xk minus the gradient of the function f at the point xk minus 1. This sk minus 1 is the vector xk minus 1. Now as this matrix dk is already prefixed, that dk is given by alpha k times the identity matrix, we take then the liberty of choosing this alpha k in such a manner that if this equality is not holding, then at least minimize the distance between these two vectors on the left hand side and on the right hand side. So we write here that in order to make dk having quasi-Newton property, that is this equation, we choose alpha k that minimizes the norm of sk minus 1 minus dk times yk minus 1. To find a minimum value of this norm, what we do is we consider the square of this norm and look at the expression. We will find that this is equal to norm of sk minus 1 square plus alpha square times yk minus 1 norm square minus 2 alpha times sk minus 1 transpose yk minus 1. Now you find the value of alpha for which this expression is minimized. You will find that the value of alpha, which we denote by alpha k, for the Barzilai and Borwein method. BB is the abbreviation of Barzilai and Borwein. This alpha k is the value for which this expression and hence this expression is minimized. This alpha k BB is given by the ratio of Sk minus 1 transpose Yk minus 1 and Yk minus 1 transpose Yk minus 1. So the Barzilai-Borwein modification of the steepest descent method is that you consider the sequence of iterates given by this iterative formula, but you take alpha k to be given by alpha k bb, where this alpha k bb is equal to this expression. And this Barzilai-Borwein iteration is although a gradient method because it uses only the gradient, not the Hessian, but it requires lesser computational work than the steepest descent method and greatly speeds up the convergence of the steepest descent method. In this paper, Barzilai and Borwein have proved that the Barzilai-Borwein iteration formula is R superlinearly convergent for the quadratic case. That means for a quadratic function with positive definite Hessian, this Barzilai-Borwein modification of the steepest descent method converges R superlinearly. With this comment on the Barzilai-Borwein modification of the steepest descent method, I now stop the lecture here, but before stopping, let me give you a few problems to be executed as home tasks. The first question that I would like to give is on the steepest descent method for a quadratic function. Let us suppose xk be the sequence generated by the steepest descent method. By steepest descent method for the function f. Then you please try to show that the step length given by the exact line search alpha k is given by gk transpose gk divided by gk transpose q times gk, where gk is a common notation in optimization methods that denotes gradient of f at xk. Then next you try to prove that the sequence xk converges to the global minimum x bar for any initial point x naught. Then third, you please try to prove that in generating this sequence xk, if we employ a constant step length, let's suppose alpha bar, then the steepest descent method converges to the global minimum if and only if this alpha bar lies in between 0 and 2 divided by the maximum eigenvalue of the matrix Q, where Q is the matrix that is lying over here. Here for the second part, the sequence xk converges to x bar is to be proven for exact step length. And in the third part, the sequence xk converges to x bar is to be proven for taking the step length to be the constant length alpha bar, where alpha bar lies in between 0 and this quantity. And the fourth part of this result is a bit tricky, that you try to find a function f so that the steepest descent method has order of convergence exactly equals to 1. So in the worst case, that is there exists a function f, a quadratic function for which the steepest descent method has order of convergence equals to 1. Here for all these problems, you please look at the book by Chong and Jack entitled An Introduction to Optimization. I have referred many a times in the previous lectures. You flip over the pages of the Chong and Jack's book, you will find that all of these results are proved. You please get into the proof of all these results. These results are really fascinating for the steepest descent method. Also, you may look at the exercise of the Chong and Jack's book on the gradient methods. you will find that there are several interesting problems given in the Chong and Jack's book. I will end up this lecture by mentioning one more result in terms of home task, that is the reduction in one iteration of the steepest descent method for a convex function. Let us suppose we are given an objective function that is convex and the function is a C11L function in the n-dimensional Euclidean space Rn, and suppose x bar is a minimum point of the function f. Now let us employ the steepest descent method on this function, and suppose the sequence generated by the SD method for the function f with a constant step size alpha k is equal to beta by L, where beta is a constant in between 0 and 1. With this constant step size, let us suppose the sequence generated by the SD method is this xk. Then fxk minus fx bar is less than equal to c naught by k for every natural number k, where c naught is a constant that depends on the initial point x naught. And this inequality is really fabulous, that at each and every iterate xk you can estimate how far you are from a minimum point of the convex function. And most interestingly, you can a priori estimate exactly how many iterations you require to reach at an epsilon neighborhood of a local minimum of the function f. And due to this result, possibly the steepest descent method is, although being most ancient, but continuing to be most popular method among mathematicians and practitioners of optimization theory. To prove this result, you may require some of the lemma that I have stated before stating the convergence rate of the steepest descent method, maybe the lemma 2 or lemma 3. In the next lecture, the topic of discussion will be the Newton's method, where the direction of movement is given by the information of the second order derivative or the Hessian matrix and the information of the gradient of the function. So the Newton method is a second order method, and this second order method, the Newton method, is the topic of discussion in the next lecture. Thank you all for all of your kind attention.